this module, you will learn about power in an LCR series AC circuit. Let us consider an LCR circuit for calculating the power dissipation in the circuit. If the voltage applied across the circuit V is equal to Vm sin omega t, where Vm is the amplitude of the applied AC voltage, omega is the angular frequency of the applied AC at time t, then the current I is equal to Im sin omega t plus phi, where Im is the amplitude of the AC current passing through the circuit and phi is the phase difference between the applied AC voltage and the AC current. We know that in an LCR AC circuit, impedance Z is equal to square root of R square plus XC minus XL square, and Im is equal to Vm by Z. Here, Xc is the capacitive reactance and Xl is the inductive reactance of the circuit. Substituting the value of Z, we get Im as in equation 1. From the impedance diagram of an LCR circuit, tan phi is equal to Xc minus XL by R. Let this be equation 2. And cos phi is equal to R by Z. Let this be equation 3. We know that the power dissipated in a circuit is the product of the voltage and current in the circuit. Substituting the values of the instantaneous AC voltage V and AC current I, we get the instantaneous power P is equal to V into I, or P is equal to Vm sin omega t into Im sin omega t plus phi. Using the trigonometric identity, 2 sin A sin B is equal to cos A minus B minus cos A plus B, or sin A sin B is equal to half cos A minus B minus cos A plus B. We get sin omega t into sin omega t plus phi is equal to half into cos omega t minus omega t plus phi minus cos omega t plus phi. On further simplification, we get sin omega t into sin omega t plus phi is equal to half into cos phi minus cos 2 omega t plus phi. Thus, the instantaneous power P can be written as Vm Im by 2 into cos phi minus cos 2 omega t plus phi. Let this be equation 4. The average power dissipated over a cycle is given by the average of the right-hand side of the equation 4. Here, only cos 2 omega t plus phi is time dependent. However, its average over an entire cycle is 0, as the average value of a cosine function over a complete cycle is 0. Hence, the average power PAV is equal to Vm Im by 2 into cos phi. Let this be equation 5. The same expression can be written as Vm by root 2 into Im by root 2 into cos phi. We know that RMS values of the AC voltage and the current are given as Vrms is equal to Vm by root 2 and IRMS is equal to Im by root 2. Thus, average power dissipated PAV is equal to Vrms IRMS cos phi. Let this be equation 6. Since Vrms is equal to IRMS into Z, we can write average power PAV is equal to IRMS square into Z cos phi. This shows that the power dissipation is dependent not only on the voltage and current in the circuit, but also on the cos of the phase angle phi between them. The term cos phi is called the power factor of the system. Let us observe the variation in the power dissipation across various AC circuits based on variation in the power factor. If a circuit has only a resistor, it is called a purely resistive circuit. In this case, since the phase difference between the AC voltage across the resistor VR and the current I is 0, that is, the value of cos phi is 1, it implies that the power factor is maximum or unity. Hence, power dissipation is the highest in a purely resistive circuit. If a circuit is purely inductive, then the value of phi is plus pi by 2. That is, the voltage across the inductor VL leads the current I by pi by 2. Since cos pi by 2 is 0, we can say that the power factor of a purely inductive circuit is 0. In other words, there is no power dissipation in a purely inductive circuit. If a circuit is purely capacitive, then the value of phi is minus pi by 2. That is, the voltage across the capacitor VC lags the current I by pi by 2. The value of cos minus pi by 2 is equal to cos pi by 2, which is equal to 0. Hence, the power factor of a purely capacitive circuit is 0. In other words, there is no power dissipation in a purely capacitive circuit. The current in a purely inductive or purely capacitive circuit, where the power dissipation is 0, is known as wattless current. In the case of CR, LC, LCR series AC circuits, there exists a phase difference between the AC voltage V and current I in the range of 0 to pi by 2. Hence, the value of the power factor will be non-zero but less than 1. Hence, the power dissipation in these types of circuits is non-zero. The average power dissipated in an LCR series AC circuit is expressed by equation 6, where the power factor cos phi is equal to R by Z as in equation 3. In this case, the power dissipation is only through the resistor. If the LCR series AC circuit is in resonance, that is, the capacitive reactance XC is equal to the inductive reactance XL, and then we know that the value of tan phi reduces to 0. This implies that the value of phi is 0 and hence the power factor cos phi is equal to 1. Hence, the power dissipation in an LCR circuit is the maximum as the power factor becomes unity. The average power, in this case, is equal to the product of VRMS and IRMS. To improve the power factor of a circuit, we often introduce an appropriate capacitor or inductor to cancel the predominance of the other in the circuit, thereby letting the impedance Z of the circuit get closer to the resistance of the circuit. Thereby, we can have Z equal to R, which implies that cos phi is equal to R by Z, equal to 1, which is the power factor at resonance. This is beneficial in many industrial applications. For example, when the distance is large, power is transmitted at very high voltages in order to minimize dissipation. This is so because a higher voltage implies lower current and subsequently lower power loss. You have now reached the end of this module. In this module, you learnt that average power PAV in an LCR series AC circuit is equal to VRMS IRMS cos phi, or IRMS square Z cos phi, where VRMS is the root mean square voltage, IRMS is the root mean square current. Phi is the phase difference between voltage and current, and Z is the impedance of the circuit. The term cos phi is known as the power factor. The current in a purely inductive or purely capacitive circuit where the power factor is zero is known as wattless current.